All right, so we are here. I'll go ahead and let me try and we have to go full screen to actually screen share with you here. Let's see. Oops, wrong thing. There we go. And okay, I bet this looks pretty trippy on the recording because probably like 3 layers of that. But okay, can you see my screen now?
Yeah.
Okay, so I've got pulled up some notes that Dr. Ford Versypt sent to me about what you guys are going to be trying to construct here in COMSOL. So can you describe for me what you're able to, what we're going for, and then we can.
Yeah, so we're basically trying to create this like system of cells within the kidney. And you can see in that little box, it's like 3 layers stacked on top of each other that are, we're trying to have glucose come in from like the bottom left there and travel up through the layers, because those boundaries between like the top being the podocyte, the membrane wall there on the second one, and then the mesangial cells.
Mesangium.
Yeah. The glucose is trying to come in and go through those because they are, I think we're saying they're permeable right now.
What's the source of glucose?
It's coming from the blood. Is that what you're asking?
Yeah, like just where the glucose is coming from, where the inflow is.
It's coming from the blood.
Biologically, just so that we make sure we have the right source for it in the model. It's helpful just to know where the real stuff is coming from, so we can pick the right representation for it. Yeah. So okay. So we'll just be doing diffusion convection, transport of dilute species through this 3 layers. Do you know any properties of these 3 layers? Like, do we need to have okay, so there's a constant concentration through all the layers to start off with?
Yeah.
Okay, is there anything else? Like, is there like a difference in density or viscosity or anything like that we would need to take into account?
I think she said right now we're just not going to worry about that. She's really, or Dr. Ford Versypt wants us to really set up the geometry and follow the sketches from the notes.
So add reactions later.
I think she wants us to worry about the boundary conditions and like the initial condition with the glucose for now.
Okay, so we start.
I'll be more comfortable so I can work on this on my own later.
Yeah, for sure. So we're going to start with an initial condition of 5 millimolar glucose. Is that what this is? Okay. And then how, do you have any idea what concentration you want to put coming in, or just put some random number for now?
I think for the glucose concentration, it says right there, we want to set it.
Am I too high?
I think that's 0. No, you're good. It's up. Right.
Oh, this is the concentration of the top surface?
Yeah.
Oh, we're going to say this is an outflow. Okay, okay. I think I get it now. Okay, so.
But I think for now, like, it doesn't necessarily matter what we set it coming in. I think that's what we're going to be messing with later, so.
Yes. Okay, so glucose can come in at this site.
Yes.
In the mesangium.
Yes.
Where can it leave? Just at the top?
Just the entire top, yeah.
Just the entire top, okay. Okay. Is there any fluid motion other than, of course, just the transport of this dilute species? Like, are we worried about water or some sort of intracellular matrix moving or anything like that? Just diffusion?
Right. No, we're just worrying about the blood right now. That's something we're gonna hit later.
Okay. Yeah. Then that's totally something we can work off with. Species, Darcy flow. All right. I think we can start going into COMSOL and see how things look. I'll keep screen sharing with you just so that you're able to actually see what's going on. This is I'm using Ultra Viewer. I'm not sure if you're using that or.
Yeah, this is what I'm using.
surprisingly quick. Sometimes it takes a second. But yeah, I'll open up COMSOL and I'll just make, of course, it'll be saved. Well, I guess I could save it locally on this computer, so you could try and move it if you wanted to, but we'll make a new model, build it, so you can see how the process goes. There's a lot of crazy stuff you can do with COMSOL, but just building this 3 rectangles of a layer, as far as some of the crazy stuff goes, it should be pretty straightforward. Right. All right, are you still able to see everything?
Yeah.
Okay, good. So we're just going to go into the model wizard. It'll just help us set things up. We're looking at a 2D simulation right now, so we're going to pick that for our spaces. So we're just going to be really looking at transport of dilute species. This is one of the recently used ones I've got, so it's an easy one here. But how you would normally find it is it would be in, I think, under chemical species, transport. Yep, right there. Transport of diluted species. Yeah. And if you wanted to, you could just like search it here, but we know what we're looking for right there. So I'm going to add that physics, or you could double click it up here, either one. And we're just going to be dealing with one species right now, so we'll leave everything the same here. Of course, as you can see, there's tons of different things you could start dealing with. Eventually, you guys will want to start adding in reactions and a bunch of stuff like that, but for right now, it's just transport of dilute species, and that's the only physics that we're going to be dealing with at the moment. So we are ready to start. We're going to click Study. And let's go ahead and leave it stationary for now. I don't think you guys really need to do anything time dependent yet. We just want to get that nice flow sort of picture. We're just going to start with that. Okay, so this brings us into the general COMSOL screen. Have you done anything with COMSOL yet, or is this all brand new?
Yeah, no, so I went through some YouTube videos and set up a like a simple like putting a drop inside of a it was like a rectangle shape, and it was
like some sort of entry flow into a pipe or something.
Yeah.
All right. So I'm gonna pull back up this. Do you know any of the dimensions for this off the top of your head?
Yeah, I've got another picture here. I can probably share it with you.
Okay. I could stop sharing and you could show me your screen.
Well, I think I can just send it in the chat here.
Okay, let me pull back up Hangouts. Oh.
Yeah, I've got it all. I can share my screen.
Yeah, just go for it. I'll stop screen sharing. So we can see yours real quick.
Okay, can you see that?
Yes.
Yeah, so the width of the whole thing is about 5.1 microns.
Width, so x-axis?
Yeah. And then that first layer is going to be like 0.5 microns for the height, and then 0.1, and then the last one 0.3.
0.1 and 0.3. Okay, I've got that written down for our dimensions. Now we can start putting stuff together. I'll start screen sharing again and go back to the actual model here. Okay, so now that we have some ideas about what we want our dimensions to be for our model, I'm just going to go ahead and start off with and just put our length unit into the right scale, so we don't have to just put a ton of decimals or anything. Go ahead and put it on micrometers. And we're going to start off with, in this tab here, so for geometry, we're going to go ahead and add rectangle. I'm going to go ahead and add all 3. And if you want to, we can go ahead and name these. Let's make this one, I'm saying geom. What was the middle layer called again? You just have an abbreviation or something, doesn't really matter.
It's the cell wall of the membrane wall.
Yeah,
So
GBM is what you have listed as there. I'll just for ease of reading. And this is
it's the glomerular basement membrane. So if you just want to call it membrane.
I'll leave it as
GBM.
Yeah, I'll just leave it as GBM for now. But okay, so right now all three of these I think are one by one and they're overlapping each other. So we're going to start with our mesangium, which is going to be starting at 0, 0, of course, just for ease. And it's going to be 5.1 microns wide and 0.5 microns tall. So we'll build that. See this, right? And then I can scale it out there. Yeah. So now we're going to start, it has a height of 0.5, so that's what we're going to need to remember going into our next layer. This one needs to be at a Y of 0.5, so that it is on top of it. And this is going to be our glomerular basement membrane. It's also going to be 5.1 microns wide and 0.1 microns thick. We'll build that, and now we have our second layer. Of course, if I had this at 0, it would just have put it right on top of the first one there. But I'm going to make sure that it's on top of it. So there we go. And now for our podocytes layer, that one is also 5.1 wide. And now we have the 0.5 and the 0.1, so 0.6 for our Y to make sure it's on top of both of those. And this one is 0.3 microns wide. So build all just to make sure everything's nice and functioning. And because these are actually touching, they have the right Y values so that they're connected to each other. This form union part here is automatic. It's going to make sure that these are considered to be, unless we tell the physics to do otherwise, it's going to consider this all to be one geometry with everything flowing through it. We can give different properties to each of these boxes, but for, say, our diffusion, it's going to be all going through all of it. There's no walls here. These are just lines as far as the model is concerned right now. Okay, so there's our geometry. We've got a good place to start off now. Now we can go into this transport of diluted species, and we're going to start thinking about how it is we're going to think about this. So first off, this is asking us which domain it's going to apply this set of equations to. We want all three, so I'm not going to touch anything, but you could say, oh, I want it to only apply to these two, and you could take this one out, but I'll add it back in because we want it to be all three. And this is going to be still just a convection sort of equation, so we'll leave it at that. For transport properties, we want to define a diffusion coefficient. I guess it's really, unless you want to do, no, we'll just leave it as it is right now. We can deal with what an actual diffusion coefficient for glucose in that environment is later. You can figure that out on your own. We'll just leave the one that they give us right here for now. Right now, it automatically puts the boundary conditions at all of these as no flux, so nothing can pass on any of those areas. We'll add some different boundary conditions in a second, but that's how it starts off with. Okay, so for our initial values, it starts in, the basic unit is moles per meter cubed, which is, of course, like 1,000 moles per meter cubed is 1 molar. But that's okay. I think we can still put millimolar in this box here, and it will, if we just tell it to convert to units, it'll work okay. I've never done it with moles. I've done it with like length scales and stuff. But okay, so 5 millimolar for our constant concentration initial condition. So 5, and then I'm going to put in brackets here our millimole per liter, and hopefully it recognizes that. I'm going to put a capital L just in case. Hopefully it's able to recognize that as an actual number. I'm going to double check by putting it in parameters here. I'm just going to call this initial condition. Initial concentration, just for, so I can double check how the units work and everything here. And here I'll put, this is 5 millimoles per liter. And we'll double check and make sure. Yes, okay, so that's the right unit conversion there. So it actually doesn't, we could have just put, 5 here. But this bracket thing is you telling COMSOL that you're putting in your own units. And it will automatically convert to the standard that the software uses. So you don't have to do it on your end. You can just tell it what units you're putting in, and as long as it's compatible with, what you're dealing with, it'll automatically convert. Like you can't put like 5 meters in this box. It wouldn't know what to do with it. But you can put 5 millimoles per liter, and it will automatically convert it to moles per meter cubed, which in this case is the same number. Okay, so there's our initial condition there. Now we need to start thinking about where stuff's going in and where stuff is going out. So we're going to start with an inflow and an outflow, right? And everything else is going to remain no flux. So our inflow we wanted to have at this bottom left, so we'll click that there, and it will only apply to this one. Now you can see if we go back to no flux, it doesn't include this boundary right here because we now have a different, it's been overridden by another boundary condition. And then our outflow, we wanted that to be the entire top, right?
Yeah.
Okay. So now we have our 2 boundary conditions that are relevant here. Just leave it as a concentration constraint. What do you want to put in as our concentration?
Let's just do like 8.
8. All right. Sounds good. Yeah, I'll just leave it as 8 now because it's the same conversion factor.
Okay.
Another thing we could go ahead and look at here is this, that we don't have a mesh yet because we haven't computed anything. But this screen would show us, of course, the all the little triangles that this would make to solve the equations over. Okay, I think we're ready to go. We have our inflow, we have our outflow. No flux applies to every other boundary. We've got our initial conditions. We've got our geometry. I think we are ready to go. So I'll go ahead and go to study and compute. And then we'll give this a second to solve over here. Okay. We probably need to do this as time dependent. Because this is there's no movement here, so this is just going to immediately this is assuming like infinite time has passed.
Yeah.
So this is going to just immediately give us a the equilibrium condition. So let's think about this. What could we do? I guess we'd want to do this as time dependent if there's no net movement of a fluid that we could consider. Does that sound right to you?
Say that one more time.
If there's no net movement of a fluid to consider, we're just talking about a solute diffusing, then we'd probably need to do it as time dependent.
Yeah.
This.
Yeah, we didn't really talk about an aspect of it, but
Yeah, so there's some, yeah, so this is, of course, because of how glucose is coming in, it's going to take this sort of profile. It's just that the model we currently have right here is not time dependent. So it's just, this is the equilibrium condition that we're seeing here. So it's right, but it's not what we want to see, right? So what do you think? What do you think we need to do? This is your project you're dealing with here. What do you think we need to do for the next step?
Well, isn't that what we were saying? We need to go back and change it to be time dependent and give it some time value for this to...
We totally could. It's just do you feel like that is the most relevant thing for you right now?
I think so. Because that's the only thing that comes to mind right now that would show us what we're trying to see.
Double check this outflow here. So yeah, I think we'll go ahead and do a new application. We're just going to do pretty much the same setup. Transport dilute species. Study. And we'll make it time dependent. Okay. We'll just leave that last one. It's simple enough. Okay, so let me just try and run through this real quick. Rectangle 1, rectangle 2, rectangle 3. We'll leave it as is. Make sure it's in microns. Go. Here we go. This one at 5 is 1. Supernet 1. I put the wrong number on that one. I did. And this one. And here we go. Okay, so there's our geometry again, real quick.
Yeah.
Initial values 5. It's the same everywhere. Okay, now we need our inflow and our outflow. Inflow here at 8, and our outflow there. Okay. Let's see here. I need to define a time step. You want to just leave it in seconds, or we want to maybe do minutes?
Let's start with seconds, see what happens.
All right. Make sure everything looks right. Okay, let's see what happens. I don't have near as much experience with time-dependent stuff as time-independent, but we're going to see what happens here. That's interesting. I'm really not sure what this means. Because it's saying that there's a very low concentration at the inlet, and then this kind of goes to a high concentration here. I'm not really sure how that happens. It's interesting. I put another. Put the arrow surface there. Sure. That was up 3. Let's just see what this looks like. If it plots, we're not giving enough information. Oh, we haven't given an expression, that's why. Concentration gradient. Huh.
Okay, so it's not going out of the top.
I'm not sure. It looks like it's weird. There's this is showing the concentration gradient. So the gradient is what we would expect. We'd expect there to be a lot of diffusive pressure to kind of get to this far right side because we have an inlet here, and then now this is the high concentration area. But that doesn't really explain why this is now the low concentration area. velocity field. There's not. Okay. I didn't think it would be. Okay. So this is diffusive flux. Huh.
Hey, I'm really sorry, Blake, but I actually totally forgot something I had to do right now. Can I come back and can we put this on pause just for a minute?
Sure, I guess.
Okay, I'm
I'll
so
look at
sorry.
I can, I guess, pause the recording and we can
Yeah,
try and figure. I'll look at this and see if I can figure out what's going on here.
yeah,
I
I'm
don't
so
know if this
sorry.
is
Yeah, I
actually
really sorry.
wrong as far as the physics is going. It's just
Yeah.
weird results.
Okay, I'll send you a message, okay?
All right, let
Okay, thank
me
you.